Alright, so I would like to also consider the following part over here. So we didn't consider this problem where we have the closed switch. The switch is closed, it means that this is just connected by the piece of the wire over here, okay? So that means that the potential difference across these 2 points is the same. So there is no potential difference over here. The potential difference is 0 across these 2 points. Why? Why? Because they're connected by the same piece of the wire, and the wire is an equipotential surfaces. We can neglect the resistance, okay? And therefore we can totally neglect that part, okay? Because the current will just flow through this piece of the closed wire over here, okay, and totally bypass this resistor, okay? Totally bypass this resistor. Totally bypass this resistor. Okay, so next part, since the current flows over here and this is just a piece of the wire, it will also bypass this resistor R3. Okay, so this will be just one single piece of the wire over here. It will completely bypass this and that resistor. And we will end up with the equivalent resistance, or with the resistance of only one single resistor R1. And therefore the answer is therefore the answer will be just 2. Okay, so the next part I want to discuss is the simplification technique to solve resistor circuits. Okay, so the first part is we need to try to apply any rules to the circuit so to the circuit below. So first of all, we need to remember that there is Ohm's law, and if we want to find the potential differences and we know the resistance and the current, then we can use this equation, or if we want to find the current, we can use this equation. If the resistance are connected in parallel, then the potential differences are the same. If the resistance is connected in series, then the currents are the same. Okay. Then we need to simplify the circuit again and again and try to apply any of the circuit rules below, and we need to repeat this step number 2 multiple times. So this sounds a little bit abstract, and therefore it's better to actually proceed with an example. So here I have an example for you. And what we need to find 3 currents shown in this circuit. So the current number 1, so it's essentially the current through the battery, the current number 2, this one is just splits from this current number 1 and goes over here, and finally the current number 3 we want to find. Okay, so we will proceed by first simplifying this circuit. This is pretty straightforward to do in this one. Why? Because we can immediately see that these 2 resistors over here are connected in series. Since they're connected in series, we can simplify the circuit into the following one, where we have an equivalent resistance for the resistor 2 and 3, I will call it A, with the resistance given by the sum of R2 plus R3, they connected in series, and in the sum it will give me 40 ohms. Alright, so the next part is we can also recognize that the resistance RA and R4 are connected in parallel, right? Because the potential difference across them is the same, and indeed, so they're connected here by the wire, so the potential difference between these 2 points is the same, and therefore the potential difference across this resistor and potential difference across this resistor is the same. So what does it mean? It means that they're connected in parallel. Alright, so therefore we can simplify this circuit by computing the equivalent resistance. How do we compute the equivalent resistance? It's 1 over RB equals to 1 over RA plus 1 over R4. Right? So they're connected in parallel, and therefore we can use the rule to compute this number over here. Very good. So we obtained that result. So now let's forget on how, let's forget how we obtained that, and now let's consider this simplified circuit over here. So now we can immediately recognize that these two remaining resistors, R1 and RB, are connected in series. We can compute the equivalent resistance and obtain, which will be just the sum. It's 4 plus 8, and we will obtain 2 ohms. Very good. So we now know the equivalent resistance of this circuit in total, in general, right? So what we need to do next, what we can do next, we can actually compute the current I1, right? So this is the only current which remains in this circuit. So this is the current through the battery. Okay, how we can compute the current I1? Well, we know the resistance, we know the potential difference. We can just apply the Ohm's law, yeah, and we take delta V, yes, and we divide it by the resistance by 12. So 24 divided by 12, we will obtain that I1 is 2 amperes. Okay, moving on. Let's now go back, go one step back and restore or just rewrite what we just obtained, that the current I1 is 2 amperes, so I just will put this current onto this diagram over here, okay, and forget about how I obtained that. Very good. So now I can proceed further and actually find delta V, the potential difference across each resistor in this circuit. Okay, I know the current, I know the current, I know the resistance. I can find delta V by using the Ohm's law, right? We know that delta V equals to the current times the resistance. Alright, so I will take 2 multiplied by 4, I will get 8 ohms, 8 volts, I'm sorry. I will get 8 volts. So the potential difference across this resistor is 8 volts. Now, so the current through this resistor is the same I1 as the current through this resistor, so the current for everything connected in series is the same, and therefore, okay, so since I know the current through here, I can find the potential difference. How? Again, I use the Ohm's law. I multiply 8 by 2, I obtain 16. Very good. So now I know the potential difference for each across each resistor. So we can move on and go one step back in our diagrams. Okay, and I use this information, so I now remember that RB was an equivalent representation of these two resistors. Okay, and here we had this current I2 we want to find and the current I3 we want to find. So now I would like to include the information which we just computed, and what we computed that delta V across the resistor RB was 16 volts. Okay, let me just include this. So it means that the potential difference between this point and this point, right, is 16 volts, because RB was equivalent resistance of these two. Okay, so the potential difference between this and this point is 16 volts. Well, if potential difference between this and this point is 16 volt, and the potential difference across the resistance RA and across the resistor R4 is also 16 volts. Yes? So, very good. Then I know the potential difference, I know the resistance, I know the potential difference, I know the resistance, I can find I2 and I can find I3. Yeah, let's proceed. I can find I2 by just taking delta V and divided by the resistance RA, so it's 16 divided by 40, I get 0.4 ampere. And now for I3, okay, so for the charge for the current through the resistor R4, I take delta V and I divide it by the resistance 10, and I get 1.6. Alright, and that's it. This is what we needed to find. We need to find the current I2, yes, and the current I3, and we previously also found the current I1. And let's just include this everything in this, transferred everything into our final diagram. So I did the transfer over here. So this is the results we obtained, and we are done with this problem.